recording on this computer starting now. All right, so welcome to all of you. And in this episode, in this video, we are going to do a small presentation, and this is on the topic of augmenting the memory. And this was a topic that Janet, who's not on the call right now, brought up because she was interested in it. And this group, as a general group, we look at topics that are related to human augmentation and augmenting memory, like just the idea of how do you enhance memory and what are different ways to enhance memory, and is technology something that could enhance memory? These are all questions that we can explore. So for my presentation today, which I decided to record so that we have some content online, it's a journal club, presentation I had done years ago. Like, I don't even remember, 4 or 5 years ago. So this is an older paper, and I haven't actually read the paper again since then. So this is just all based off of the PowerPoint. So I may like mess some things up or forget some stuff, but I think it should be good enough for sort of our general exploration of the idea. So here it is. This is, I always like to start off with a fun picture, and this is a sweet potato that has veins on it, and it kind of reminded me of a muscle. And since I'll be talking about motor stuff, that was very relevant. And the paper I'll be talking about is called The Dissociable Effects of Punishment and Reward on Motor Learning. And again, we were talking about sort of augmenting memory, and one of the things I want to explore is motor learning, and to a certain extent, motor memory. And the question, how do we augment? How do we improve motor learning and memory? So just as a very quick introduction, there are many different types of motor learning out there. Two of the types that have been studied quite a bit are motor sequence learning, and motor sequence learning is like playing the piano. So like, in these experiments, what they sometimes will do is that they will have like a keyboard or something, and then they'll be like, press it in this order and memorize it, pressing in this order. And then they look at people, who can actually learn this, and how long does it take to learn this, and what sort of interferes with it, and what sort of helps with it. And they've actually done brain scans, which is what's really cool about this diagram. So in motor sequence learning, you can kind of see there's a fast learning period, and there's certain parts of the brain that are activated. Then there's a consolidation, and then you go into slow learning, where you begin to refine what you've learned, and you go through a process of automation. In the beginning, you may have to think about, this is the sequence that I need to play the piano, but eventually you sort of automate it, and you no longer even have to think about it, and your fingers just sort of do it, which is kind of cool. So people have studied that, and they've looked at the different brain regions. The other type of motor learning that people have explored, and again, you could say motor memory, because like if you're playing the piano, you're not really thinking about it. That's sort of the motor memory, is motor adaptation. And this is what we're going to talk about today. And motor adaptation is kind of interesting. It has to do with your muscles. Some people call it muscle memory, which is not really a good term in many ways, because the memory is not being stored in your muscles. But that's the sort of general idea where many of these things fall in. And I'll just give you one example of where this is practically applicable. Let's say you're playing basketball, and you're trying to shoot those hoops or whatever, you've got the basketball and try to shoot it into a hoop. And in the beginning, you're really good. But eventually what happens is your muscles actually begin to fatigue, you get tired. And as a result, they're activating in a very different way. And if you want to keep shooting those shots in, you actually have to go through a process of motor adaptation. You need to sort of, the way you activate the muscles is going to change. And you need to be able to do that on the fly. And that's sort of the idea of motor adaptation, where the way you're controlling the muscles is actually changing over time. And that, you could say, is a type of memory. The first thing I'm going to show you is an actual video from the lab that I work in, the Ashton Gravio Spatial Orientation Lab. And what you're going to see is that this person's walking into our very famous rotating room. And not too many people have experienced this, but Punya, who's on the call, was in the lab working, and she was able to experience this. So here, this person is showing you that when you're in a rotating environment, and this rotating room can spin quite fast, but we usually operate it at around 10 times a minute. And so it's spinning, and she is sitting in there. It looks like it's not spinning, but it is. And she's throwing balls. And you can see it's a weird environment when you're in it. You can see that the ball sort of, when she throws it, veers off to one side. It doesn't go straight. And what's also interesting is what she's going to do here, she's going to sit, and this is actually very like important work that came out of our lab. It sort of, in my opinion, started like a whole branch of research out there that many other investigators have looked at. So she's going to just try to reach and touch this square. That's her task. Very easy to do in normal life, but what you're going to see is in a rotating environment, her finger is way off because the Coriolis force is acting on it and it just deviates. And then over time, she is going to keep reaching and she's actually going to be able to hit the target. Now, oh, it stopped. So what I should also say here is that that's kind of like a memory, right? Because at first, you're consciously trying to adjust your muscles, but eventually your nervous system learns that in this rotating environment, I need to activate the muscles in a different way so that I can reach the target. It's quite extraordinary if you think about it. It's able to do this within like 40, 50 reaches. And that's really pretty amazing. And after that, you don't have to think about it. You know, it's all automatic. So this is a type, again, of memory. And this is just some quick data. You got trials on the x-axis, and then on the y-axis is endpoint error. So in the beginning, the rotating room is off, and you're just reaching, you're doing a great job, you have 0 error. And then you turn the rotating room on, and all of a sudden people are doing really poorly. They're really far off. And then as time goes by, they're able to adapt. They go through that motor adaptation and their endpoint error gets better and better and better. And then, and this is the crazy part, you turn that rotating room off, you bring it to still, bring it to normal life, and people are not able to deal with that. So if before your arm was deviating this way, you learned to deal with it, now all of a sudden, when the rotating room stops, you have an after effect in the opposite direction. So now you have a memory, you could kind of say it, in your nervous system of the rotating environment, and you have to relearn how to reach in normal life where you've been your entire life. So it's an interesting, very different paradigm. What you can also do is do the exact same task, not in a rotating environment. You can do it sitting in a room holding a robotic handle. And what this handle does is it pushes your arm in one direction. And then you need to, over successive reaches, be able to adapt to that weird force that's pushing. This is a velocity-dependent force, just like the rotating room is. And so a lot of investigators across many universities have this device, and they study this as a way to understand motor adaptation in the human. And so the final type of, or maybe not the final, but another type of a very similar perturbation is here and this is the one that they use in the paper. Here the person is sitting, and you have a start point and you have an end point. And your goal is just to move the cursor to the target. And the person, their hand is hidden underneath the table, so they can't see what they're doing. They can only see this computer screen. And so, and they have like a handle, so the handle has a sensor on it. So initially, when they're moving the handle straight, the cursor moves straight to the target. But then what they do is they do a visual motor rotation. And all that means is when the person moves the handle straight, the cursor goes off at a 30-degree angle. And now this person has to adapt to that. They basically have to learn, oh, I need to push the handle 30 degrees to the left, and then the cursor will go straight. These are just different ways of messing with people and seeing how does their muscles and their nervous system adapt to these things. Now, you might think, oh, this is kind of contrived and who cares about this? But it turns out that people have used this very simple paradigm to study all of these different topics. And I won't read through all of them. I'm just trying to show you that this is a cool paradigm that a lot of people have done. I'll skip through this just because it's a little bit technical. So the paper basically asked the question, for this task that I just described, will giving feedback that is reward or punishment influence motor adaptation? If you're being punished, are you going to learn to reach faster when you've got this weird perturbation on you? Or if you're rewarded, are you gonna learn this better? What is better, reward or punishment? So I would say come up with your hypothesis, and then you're gonna find out. And again, whatever hypothesis you come up with, it's important to say that's very specific to this experimental paradigm. More experiments need to be done to see if it can generalize. And maybe people have done it since then. I haven't actually looked at what people have published afterwards. So, okay, as a quick reminder, people cannot see their hands. And all they see is this virtual image where they have a square, which is a start point, a circle, which is the target. And then they just have to reach towards it. And they're reaching underneath the table. And then what they see, and oh, I should also say the target changes locations. So they want to make this a little bit difficult. And then what you see is as you try to move, in this case, there's a 30-degree rotation. So when the person moves straight, the cursor goes off 30 degrees and the person sees it. They're like, whoa, it went off 30 degrees. And then they get at the end a yellow dot that says, look, you landed here, you made a mistake, and you fix yourself. So that's sort of the information they get. There are three groups. There was a reward group, a punishment group, and a random positive group. The reward group, if you hit the target, you got a lot of points. And if you didn't, you got fewer points. And if you collected enough, you got money. So that's a really great reward. The punishment group, same thing. If you hit the target, no punishment. But if you did not hit the target, then you got negative points, and that took away from your money. And so that was punishment. And then the random positive group was just a random number that had nothing to do with anything. Okay, so which group is going to learn the task the fastest, reward or punishment? So what we see here is, so this graph is a little bit different. On the x-axis is trial, and then on the y-axis is reach direction. In the beginning, it's a baseline. There's no rotation. The person is just trying to reach forward, and then that's it. And you can see all the groups, the random, the reward, the punishment, they all are pretty good at reaching that origin. And then what happens is they apply that 30-degree rotation. So now they have to learn to be able to reach 30 degrees in order to go straight. And again, there are multiple targets. So this actually takes a bit of time. You can see everyone takes a bit of time to reach that 30-degree point. It almost looks like no one is able to perfectly do it. So what you see here is the black line is the highest. They're the ones who are able to do the task the best. And that's the punishment group. So only the punishment group leads to the faster and better learning. Okay, so that's kind of scary, that punishment, and then we can talk about this. Like, do you think this would work for other stuff? Do you think there's some negatives towards this? It's kind of an interesting thing. And the other stuff is the next question they ask is that, okay, you do this. Now what happens if we take away all feedback? There's no visual feedback. They can't see what they're doing. There's no reward or punishment. Do they keep that adaptation of moving 30 degrees, or do they change it? What do they do when they get no feedback after they've gotten this training? And what you see here is that the red group, the reward group, holds on, you could say, to this learning the longest. So again, I mean, what does this really mean? But in today's language, in today's presentation language, we're talking about memory augmentation. You might say this is sort of like a memory, like you're not getting feedback. You're retaining maybe some memory that there was a rotation, and the people who got the reward were able to retain that a bit longer. So that's interesting. And again, like, can you augment your memory just by getting rewards and having positive feedback and reinforcement? Are these things that we can think about? So reward leads to greater retention. Okay, and and I'll go through the rest a little bit quicker, just because there's several things that they did, which is cool. They were re-exposed to this exact same rotation, and the question was, who will relearn it the fastest? And you may maybe have guessed, the people who got the punishment were the ones who were able to relearn it the fastest. Now again, is this also a memory that you learn it much later? Maybe hard to say. But it's interesting. It's kind of interesting. Okay, then they said, what would happen if would anything change if subjects reach towards only one target as opposed to 8? And you can see that if you only have one target, people learn wicked quickly. But again, they see that the punishment group is learning faster and better. So that's something interesting. And the reward group, again, like when you turn off all of the information, they seem to retain this information for longer over here. Does a binary monetary punishment affect anything? So now instead of having multiple points you only get 1 point or you get nothing. And what they find again is that punishment, even with binary, leads to faster and better adaptation, learning this motor memory. So that's also kind of interesting. And again, you have to think about like punishment and what types of punishment. There may be some punishments that would work and others that really don't. Okay, is punishment feedback or the loss of money that affects learning? So here they were like, okay, is it the punishment or is it the fact that you're losing money? Which one is it? So, the next group was they were given punishment feedback, but they were told that you're going to get punishment feedback, but it's not going to affect how much money you get. So what happens? Well, it turns out that in black over here, punishment independent of money is enough to lead to faster and better adaptation. It even catches up with just the normal binary. It turns out that even money as a motivator is not enough. It's just the bad, you didn't get it right. That punishment that maybe, I don't know, accelerating learning. It's actually pretty interesting. And is it just punishment or meaningful punishment that leads to better training? Maybe, I don't forget what they call it, the machoist or sadist. I don't know, whatever. There's a terminology for people who just like punishment. So the question is like, is it just raw punishment or does the punishment really have to have meaning? So then they had a random negative group. You just get random negative feedback, but it doesn't have any relation to your performance. And what you see is that they perform the worst. So it's not randomness of punishment, not punishment alone. It really is punishment with meaning that seems to be driving people to learn this task a little bit better. Okay,
what punishment did they use when they said it doesn't have to do with money?
I think they still got the binary, negative points that they saw, but it didn't reduce their monetary value. It's a good question. I think that's right. I haven't read it in years, but I think that's what it is. Okay, so here are my summaries. Punishment feedback, not reward, leads to faster and better adaptation and savings. Does not have to be graded or have monetary significance. It has to have meaning. It has to reflect the error. Punishment feedback enhances the short-term process. This is error-based learning. Now, I'm going to read this. I don't really remember what I wrote here, okay? But this makes sense. A lot of the early is error-based learning because you see, oops, I didn't reach right. I need to fix it. And the cerebellum is important for error-based learning. And studies with imaging and cerebellar patients sort of confirm this, and it detects the difference between intended and actual actions. So the cerebellum is sort of like, some people say it houses the internal models for motor movements. If you make a mistake, the cerebellum is like, oh, I should have been here, but I was here. And then it tries to use that feedback to update the internal model. Okay, so perhaps punishment feedback enhances the cerebellum's error-based nature. And that's in the early stages of learning, maybe, Reward feedback leads to greater retention. That was something that we had seen in the study. And by retention, they meant slower rate of decay. And another paper says that some of these types of retention can sometimes last for hours, maybe even days. So the idea is that reward feedback enhances the long-term process. M1, in the motor cortex is essential for retention of motor adaptation. And we've seen this in monkeys and human TMS. And TMS is where you take like a transmagnetic stimulation, where you take like a magnet, like a mini MRI, and you just pulse a magnetic pulse through the brain. And it can either enhance a portion of your brain or knock it down for a little bit. Okay, so they've done that with M1 and seen, oh yeah, looks like M1's pretty important. And there are dopaminergic projections from M1 that are needed for retention. And dopamine is used often in reward feedback. So you might be like, okay, error-based learning, cerebellum, punishment in the first stage, and then an idea might be longer stage, retention, learning, reward, dopamine, and so that's why reward is working. These are all just like, I don't know if this was in the paper's discussion or I came up with this. This was years ago. So, take this with a grain of salt. Okay, cool. And this is actually, I show this picture of a question mark in all of my presentations. And this picture I actually took in India. And this was on a beach. And I found this little creature and it looked like a question mark. And I put this seashell right at the bottom to make it look like a question mark. All right, so there are only four of us here today. So maybe our brainstorming session will be short and sweet, but hopefully it'll be a little bit longer than short and sweet. And let's get some wild ideas into this brainstorming session. Any interesting wild ideas that you guys have to flower this flow chart that I have? Anything from, like, since we talked a little bit about technology, any thoughts on how technology could administer punishment for different tasks or reward? Any ideas there?
Actually, can I cut in or?
Oh, please, man. Yeah.
Yeah. So actually, I'm a little bit confused. Like, is this something like you have already finished as an experiment, or is it a proposal?
No, this is actually an experiment that a different group has finished. So this is all published, on you can get it on the internet. So this is the actual paper here, and they published this.
Okay, so like, so generally you are designing, so you're based on a research paper and try to present it, or?
Yeah, so I think for these series, what we've been doing is each of us have chosen like a research paper on loosely associated with the topic of augmenting the memory. Yeah.
Okay.
Yeah.
Okay.
Yeah.
Right. Yeah. So okay. So this one is trying to say that a designed punishment can, at a great extent, help people to like benefit on their memory. Is that?
Yeah, I mean, that could be one, I'll put that in. That could be one sort of thought that we have based on this, which is that, could punishment help in, accelerating learning in like other tasks? Now, this task was a very specific task, and would it improve other things that we do, such as the PhD program that you're part of, Manning? If you start getting a lot of negative feedback.
Yeah, I get it. Like, so this paper trying to say that like punishment overweights benefits or like gifts in augmenting people's memory in these specific tasks. Is all right? I don't know whether I get it.
Yeah, no, I think that's like a somewhat fair takeaway, that punishment can help in accelerating learning for this reaching task.
Yeah.
Yeah, that would be one thing that maybe they would say.
Yeah. So like for me, my biggest question is this task unbiased or biased? Like, so if we want to reach this kind of general conclusion that punishment can help augmenting memory, then we should say whether this experiment can be generalized to all other like human actions or movement kind of things.
Yeah, I mean, Manning, I really like that, because that's a really great point. And so we would have to try this in other domains and other like learning paradigms and see how much this is generalized. Is it just this weird reaching task where you have a computer screen that's changing the way that you're reaching?
Because to me, like a very big division between psychology and sociology is like we usually do not use experimental methodology to test things out. We usually just observe and to see what is the natural, like in a natural setting, probably not natural, but in a social setting, which is not like a man-made kind of environment. How will people do? So basically, I just feel a little bit doubt and concerned about like whether this setting can be generalized to all like human action, because like I mean it is the human beings that this experiment aims at, right? So he like the researchers designed this experiment to see whether there is a relationship between punishment and human memorizing kind of actions. But what if like this kind of experiment is like it is not, yeah, just cannot be general or something. Sorry, I'm a little messy here.
No, Manning, I really appreciate that. And I think the 2 points that you brought up that I really liked is, number one, can it be generalized? Because like even for motor adaptation in a more like basketball playing, where you have multiple elements there, motor adaptation, but other types of learning, what happens? Maybe punishment will actually screw you up a lot more. And so like really, what are we examining by looking at this paper? So I think generalization is really important. And I think also like technique is really interesting, that you come from a background of sociology. And so that's a lot focused on observation. And it may actually be an interesting marriage. And I'll put this over here, where we take some of these ideas and then we sort of observe it in like a very complex, task where it's really hard to measure stuff. But then that's like the real life, that's the real world. So that might be, that's like, I really like that idea. Marry these two fields and see if the idea, let's say observe in a very complex environment, whether these, findings. So that's really cool. I appreciate that. Nice.
I also wanted to bring up the question of certain personalities and how that changes punishment and reward, because it could be that a certain type of personality understands punishment and doesn't take it to heart, so that's why they're improving more, because they know that it somewhat motivates them. But a reward could help somebody else more, or a punishment could be taken to heart and really cause someone to be dejected or something like that. So
yeah, and actually this actually connects to a lot of the sort of like studies that we had done with the phototactors, our study with the phototactors. Because like it's not really well understood, like even with motor adaptation, whether some people be very resistant to it or whether some people would be okay with it. I mean, these are all that we see in this presentation. If you look at like their data, is like average data across I don't know how many people, and you get a little bit of these bars around it. So maybe you get some sense of how much deviation there is. But it would be really interesting to see whether these things hold up with different types of people. And sort of adding on to that, sorry, but like I think this is really great. Like, what kind of surveys would we create? And that really connects in a way to what Manning was saying with psychology versus sociology. Could those like inform some of these surveys and the questions that we ask? But that's really deep. Any other sort of thoughts or things like that? Yeah, Dhananjay.
I wonder what would happen if you tried the same thing, punishment versus reward, but with certain tasks that already have inherent punishment in some sense. Like if you're balancing, like there's the risk of getting hurt when you fall, or say like you're trying to like obtain the reward as the task itself, then how would that change the difference between, and would there even be any difference between the two groups then?
This is really good. I only got a little bit because I was thinking, where did I put the point of generalization? I may have forgotten to put that in. So and then oh, maybe this is kind of the same point as this. Okay. And then Tanmay, you said, what if the task has already inherent qualities? What if task has inherent qualities of punishment already in it? And this is actually, a really interesting task question, because I've talked to this with my advisors. And in my lab, Manning, you may have seen the machine that I use. but I strapped blindfolded people into a machine and they had to balance themselves.
Yeah, I see it.
Yeah.
You sent me, right?
There, I've shown a video, yeah. So that has like an inherent quality of punishment, because when you hit the crash boundary, it really just is not pleasant and you are not happy. And then you're sort of coming back up and you're just like, you're feeling like you feel viscerally, kind of like a failure. I don't know. So my machine versus sort of visual inverted pendulum. And this is the task in the lab that some undergrads are looking at, where it's just a pendulum on the computer screen and you're using a joystick to keep it balanced. It's very similar to my machine, but now all of a sudden, if the pendulum falls, you're just like, oh, who cares? And does that matter? That inherent punishment is missing, and are the learning rates different? Tell me, was that sort of what you were saying? I'm not sure if I captured everything that you said.
Yeah, that was exactly what I was saying.
Yeah, I think that's really, and it is very frustrating when you had said what do you mean? What was frustrating for me?
The inverted pendulum. Like, I've never tried your machine, but I'm sure it's even more frustrating because you're physically getting hurt. But I was banging the joystick and it was just mentally frustrating, but I couldn't.
Yeah, what happens when punishment leads to frustration? The other sort of things, like in my machine's different, right? Because like it can also induce anxiety, because you're like, whoosh, and then you're like, whoosh, and it's not, so anecdotally what I've found is people who are prone to anxiety do poorly. And it may be that if you have high anxiety, this maybe it connects some of the things that we're talking about here with the individual differences and anxiety. These things, you may have a reaction to punishment in a different way. How do I connect all this? This, and then we can just put anxiety here. So that's really pretty interesting. All right. This is a pretty good map over here. Any like other ideas, like more far out? Like how about an art idea? Something with art. What could it be?
I mean, I guess it'd be cool to see what people would paint, how it
Yeah.
differs after the different stimuli or whatever, like the different reward versus punishment. If they would, use more angry colors, splash harder, something like that.
Yeah, or what if we even looked at, so artwork and reward and punishment, and also sort of like just look at the trajectory. Are the movements of people who are punished, are they reaching in a way that's slightly different? And you could turn that into artwork if you found something statistically different in their trajectories. That might be kind of interesting. And Manning says that sounds cool. So that may actually be interesting for any sort of learning. You punish people and you reward them, and you see how does their movement change. And again, like, this is another slight topic, but people say that like my brother used to say I had the loser's position every time I'd lose in video games against him, because he's 6 years younger than me. And even before he hit puberty, he was able to beat me in like all sports, all video games, everything. And so he'd say I'd go into my loser position. But I mean, there is that, like when you lose, when you're punished, your posture might change. I feel like I've heard that. So does posture change with punishment? Failure is another thing. So I think also maybe now we can explore this idea of memory augmentation too. So right now we've sort of been talking about the paradigm. So one thing maybe from the paper, and even that wasn't very clear, was that maybe reward actually helps keep that motor memory alive for longer. So punishment will allow you to learn quicker, but then reward is what allows you maybe to keep it alive for a longer period of time.
There's
like,
sorry, go ahead.
no, please go.
Yeah, I mean, I was thinking also like, can you train memory to react the same way, or can you augment it to react the same way to different types of stimuli, whether it's reward or punishment, or how harsh the punishment is?
Train memory. So
I mean, at the moment, punishment was seeming like it helps people learn better, and reward is long term. But can we make it even somehow?
yeah, can you train?
AI Manning.
This is actually really quite. It's really. What did Manning say? Yeah, I mean, Manning, that's really deep because like here's like a crazy idea that people may do, which is that like, what if you sort of have an an AI is attached to you, always watching you learn, and then based on what phase of learning you are, it could be early or late, you know, for early, it gives you punishment, and for late learning, it gives you reward. I mean, how insane would that be? It sounds like a scary futuristic thing, but it could definitely, it could happen if people find, let's see, and it's creepy, it is. And I kind of feel like I saw an anime, I forget what it's called, but I definitely, saw an anime where based on your emotions, the AI injected you with chemicals to always keep you balanced. It was an interesting premise, but it's sort of similar. Like, what if we totally understood motor learning and we knew particular types of reward and punishment are are going to lead to enhancement? I mean, would you guys want to have like little AI sitting on your shoulder giving you like reward or punishment based on what phase of learning you are, and then you become like a super learner? uh, is that something you'd want to do? We could design that. Who knows?
One other thing that AI thing makes me think of is I think there's like a type of reinforcement learning where the algorithm itself, the model is trained when it has like its own reward system. So I guess comparing that to how a human reacts differently, I don't think an AI would like react differently, since like it's just mathematically like subtracting the failure to get the same result as adding the reward would be the same, but it would be interesting to compare that to a human.
Yeah, or so like a lot of AI, it's actually kind of interesting. I did a podcast on this, which I never published, with like a computer science grad student. And one of the things with AI is that the early stages are making these neural nets, and some of it was inspired by biology, and then for a while they sort of were not doing biology inspired, and then it sounds like they went back and sort of looked at things like backpropagation and things like that, and they began to incorporate it into it. And so, there is a trend sometimes in AI to look at human behavior or whatever, neural behavior, and see if that enhances stuff. So just to add on to, does having this human quality in AIs lead to better performance? Is it good that we have these different ways of like learning motor memories? Maybe different brain regions are activating and they're motivated by different types of stimuli, or is that just something evolutionarily silly that happened in us, but an AI will do much better without having these things? It's a really interesting question. Yeah, that's a deep thought then. Nice. All right. Any other? This is actually this is a good spread. This is a good spread. We got a little taste of art in here, and then we got a little taste of AI in here for retaining memory. And we came out with our very creepy augmented memory, idea, which we could try implementing. We could try building it, or we could make like a little scary creepy video of this idea.
Yeah, it'd also be interesting to look at the I don't know, the neuronal differences as to why this happens, like what is actually going on in the brain and how the brain. I mean, I haven't looked into this, but reward and punishment in the brain. So I don't know, biologically.
Yeah, and there is a
Also
sorry.
sorry. Oh yeah. Also, I just wanted to say that the time frame in which punishment or reward is administered could make a difference, because if it's, you know, multiple times, or you know, every second they make a mistake versus, you know, every five, or the punishment isn't as harsh sometimes versus like a reward every second, or a reward after you reach a big goal, you know, so you're looking up to it, things like that.
This is like really deep. I mean, yeah, honestly, I didn't even think about that. And it's a really great point, which is what is the optimal time scale of, these stimuli? I mean, it's a really good question. I mean, do you need it every single time, or do you need a little bit of exploration? And so, people have looked at all sorts of different stuff in sports and other things too. So it's really fascinating. But it's a great question. And for your neuronal stuff, so there are a lot of human imaging studies, and then there are a whole bunch of animal models where they use optogenetics and stuff like that to like just stimulate one circuit or whatever for reward and see what it does to behavior. So there is a lot of like, there's a whole universe of work, most of which I don't know, um, but it's interesting. There are also a whole bunch of stuff where like, they'll take like Parkinson's patients and stuff like that who are on drugs that boost, so the Parkinson's will lose their dopamine, cells, so they get like extra dopamine. So what they do is in some of these experiments, they have them not take the medication, and they see like what does that do to the person. It's interesting. What does that do to your reward system? So there are some of those type of studies too. Um, okay, this is really good. Maybe I'll put the Parkinson's thing in here too because it's kind of interesting. And then maybe this is our study. Okay. Any other final thoughts? This is good. This is really good. We got a really cool. I really like this flow chart. This is good. Sweet. Thank you, Henning. It is a very pretty map. I always enjoy doing these. So nice. And so, Punya, no stress because you're going to be starting undergrad, for the first time in your life. So are you sure you want to do a paper for next week, or do you want to like, if school gets too intense, then not do it? What are your thoughts?
I mean, I think I should be able to do it because my classes don't actually start till the 1st. So, and I'll do it before I leave, obviously. Like I'll do the present. I mean, I'll write it up and I'll read the paper.
Okay.
So yeah, I think I should be fine, but I'll let you know. Like maybe someone can get ready as a backup. But I should be.
Yeah. So don't feel any stress. If something comes up, then don't worry about it. If you get it done, then we'll do it. Otherwise, maybe we'll do a chill session, or maybe I'll have like a backup question on there. Okay.
Yeah.
Sweet. All right. Well, awesome meeting, and I will